Alright, welcome to a chi-square test. The chi-square test is used to see if a predetermined ratio was actually accurate by using a sample. So here we have a ratio of squirrel colors. The known values here are that 70% of squirrels are gray, 20% are black, 10% are red. Alan thinks that the squirrels at the Findlay campus have different ratios, so he takes an actual sample. He gets 29 gray, 10 black, and 9 red. These have slightly different ratios than these, so we want to know if that's significant enough to say that that these ratios don't work for the UF campus. So we're testing Alan's hypothesis with a level of significance of the standard 5%. So here, our null hypothesis is just these pre-known ratios. So we've got the first ratio is 70%, the second one is 20%. Third one is 10%. The alternative hypothesis for this type of test is always that at least one of those proportions is wrong. So now we need to kind of make a list of the data that we've got. We've got 29 gray squirrels. 10 black squirrels and 9 red. Those are the observed values for the different categories. The expected values are whatever our sample size is. Our sample size here looks like 48. So we take 48 and we multiply it by each one of these proportions from the null hypothesis. That's what we would expect to get out of each of these samples. So 0.7 times 48, 0.2 times 48, 0.1 times 48. So this is what we would expect to get. This is what we actually got. The chi-square test is essentially testing the difference between those. So now we can actually figure out this chi-squared statistic. To do that, we're taking the difference between the observed and the expected values for each category. We're squaring that difference, dividing by whatever that expected value was, and then we add all of those together. So I guess let's figure out the difference of each one of these first. 29 minus 33.6. 10 minus 9.6. And 9 minus 4.8. So this is observed minus expected. I square that for each one of these. And divide by the expected value. So let me do all of that. So I take each one of these, I square it, and then I divide by the corresponding expected value. The first one I get about 0.63. The next one is about 0.02. And the last one gives me 3.68. Notice this last one is the largest out of them, and that's kind of the one that was off by the most. The chi-squared statistic is just adding all of those together. I get 4.33. So that's the value for chi-squared. That's what I want to test against my level of significance. My chi-squared distribution looks roughly like this. That alpha of 0.05 is that tail of that distribution, which is always on the right for these. So I've got a 5% probability in that tail. I want to know if my chi-squared statistic falls in that critical region or not. There's a separate table for looking up chi-squared values. For that, I need the chi-squared value or a probability, and I need that degrees of freedom. For the chi-squared, degrees of freedom are k minus 1, where k is the number of categories. For this particular example, I've got 3 different categories, so my degrees of freedom is 2. Alright, so alpha 0.05 and degrees of freedom 2 gives me a chi-squared value of about 5.99. So this is the chi-squared value for my level of significance. I compare my chi-squared value, 4.33. It's not in that critical region, so here I'm failing to reject the null hypothesis. I can also convert my chi-squared value into a probability. So if I take my chi-square of 4.33, my degrees of freedom at 2, I can convert this into a p-value. Again, I'm looking on that chart. For the chart I used, I couldn't get very much accuracy out of it, but it did say that my p-value would be greater than 0.1. So since my p-value is greater than 0.1 and my alpha is at 0.05, I know my p-value is more than alpha, and again I fail to reject that null hypothesis. Alright, so that's it for that one.